perhaps one of the first offline events here in IBS, at least with our two groups. So it's our pleasure today to have Professor Wojciech Samotij from Tel Aviv. So let me just briefly introduce Wojciech. We actually had the same PhD advisor. He graduated, finished his PhD at Illinois about a campaign with Joseph Pollock, and then did a postdoc at both Cambridge and Tel Aviv. Now he's a faculty at Tel Aviv University. He's one of the authors of these hypergraph containers, which is considered to be one of the biggest breakthrough in the past decade in combinatorics. So, and Wojciech obtained numerous prizes, including the prestigious European Prize of Combinatorics and others. So without further ado, let me give it to Wojciech to tell us everything about hypergraph containers.
Thanks for this. And welcome. Thanks for coming. Good morning. So in this 5-meeting course, I'll try to give you kind of a crash course or some gentle introduction to the method of hypergraph containers. And I hope that also the exercises will help you to maybe explore it a little further. And I'll try to keep the technicalities to kind of the bare minimum that is necessary. And maybe one small request is people here in Korea are kind of much shyer and more polite than what I'm normally used to. Please don't be afraid. If you have any questions, something is unclear, just raise your hand or just feel free to interrupt me. And I mean, we're a small room, so I would really like to address all your concerns. Okay. So what will be the goal of the course? The goal of the course and kind of the goal of the method of so-called method of hypergraph containers is to understand families of discrete structures that satisfy some collection of local constraints, or constraints involving just few elements at the same time. And instead of kind of giving an abstract introduction for the first 2 or 3 meetings, I'll focus on a single example that is probably familiar to most of you, if not all of you, and these are triangle-free graphs. So our main example, it will be the family, which I will denote by script F, and of the triangle, and these are triangle-free graphs. On the vertex, on any vertex set of n elements, and the canonical choice here would be the first n positive integer. So all labeled graphs with this set of vertices that don't constrain the triangle. And if you've taken any course in maybe slightly more advanced course in graph theory or extremal combinatorics, you probably know at least one result about this family. So classical results concerning this family. So the two I would like to discuss, the first one is so-called Mantel's theorem, which is now over 100 years old. I think it's 1907, which states among all graphs in this family, the one which has the most edges is the balanced complete bipartite graph. So you take the vertex set, you split it in two, you keep only the edges in between. This graph doesn't have a triangle because it's too colorable, and the triangle is chromatic number 3. And the theorem states that this is the unique triangle-free graph with the largest number of edges. So to write it more concisely, we can define the so-called extremal number or to-run number of the triangle, which is actually not a number but a function. It takes n as an argument, and this is defined to be the largest number of edges in a graph from this family. So this here is a definition. And the theorem says that this is equal to the maximum number of edges in a bipartite graph. So we split the vertex set into k and n minus k vertices and keep all the edges in between. And this, as we learned in high school, maximizing a quadratic function, this maximum is achieved when k is close to n over 2. And this is the graph. Moreover, the complete bipartite graph k and half is the unique extremal graph. So it's the unique graph which achieves equality here. Okay, the second theorem, which also most of you should be familiar with, is the theorem of Ramsey, which states that if I take a sufficiently large complete graph on n, so n vertices n sufficiently large, and I color all of its edges in R colors, then in at least one of the colors, I need to see a triangle. So Ramsey's theorem. Which states that for every integer r, and any coloring of the edges of Kn of the complete graph on n vertices with our colors contains a monochromatic triangle, provided that n is sufficiently large as a function of the number of colors. But why did I say that it's a statement about triangle-free graphs? Because you can rephrase it in an equivalent way. You can say that the complete graph Kn cannot be represented as a union of R triangle-free graphs. So if a coloring existed so that in our colors, so that every color wouldn't contain a triangle, then every color would be a triangle-free graph. So this is equivalent to saying that they cannot represent Kn as a union of R graphs from the back. So equivalently, it is not true that we can find graphs G1 up to GR, which are triangle-free, such that Kn is their union. Again, provided that n is sufficiently large. Now, kind of the topic of this course, and one of the goals here would be to say we have some statements that involve triangle-free subgraphs of the complete graph on n vertices. And we would be interested in proving analogues of these statements where we replace Kn with a different graph, namely a typical graph. So a random graph with a given density. So the course we will prove analogous statements with Kn replaced by a typical graph. Now, there's kind of one canonical model of a typical graph, which is kind of intensely studied. It's maybe the easiest to study because of the independence property, and this is the binomial random graph. That is sometimes called the Erdős-Rényi random graph, even though it's not the Erdős-Rényi random graph, because the Erdős-Rényi random graph is a slightly different but related model. So let me define the model. GNP is the binomial random graph with n vertices and edge probability. And if you haven't seen it, let me define it. This is a random graph, which means it's a random variable that takes values in the family of graphs with n vertices, and it can be most easily described as the outcome of the following random process. Kn, the complete graph on n vertices, has n choose 2 edges. And now for each of these edges, we toss a coin that comes up edge with probability p and non-edge with probability 1 minus p. And we do it sequentially and independently for all the edges. So for every edge, we decide with probability p. So for every pair of vertices, sorry, we decide with probability p it's going to be an edge of our random graph, with probability 1 minus p it's not going to be an edge. And this is independent for all pairs. So the vertex set of G and P, again, we will assume that these are the integers 1 to n. And now every pair ij of the vertices forms an edge with probability equal to p independently, meaning independently of all the other pairs. And the question or questions that we would like to study is, when does the conclusion of Mantel's theorem hold relative to this model? Meaning, for example, when is it true that the largest triangle-free subgraphs of GNP are its largest bipartite subgraphs? Or when is it true that you cannot decompose GNP into a union of R triangle-free graphs? So, under what assumptions? On P, which we also allow to be a function of n, does the conclusion of the Mantel's theorem or Ramsey's theorem hold relative to GN. Now, these kinds of statements kind of have been proved and have been studied since late 80s roughly, and there's been a lot of results and a lot of developments, and I'll tell you a few things about one approach to addressing these questions. And in this course, we'll be able, for example, to pretty early on to prove a version of Mantel's theorem relative to GNP and a version of Ramsey's theorem relative to GNP. Will even prove some of these statements as part of your exercises. Okay. So before we continue, let's try to understand what we're really asking here, because it's not a kind of a formal mathematical question. What do I mean by a theorem which is relative to GNP? So let me start with Mantel's theorem, more precisely. Here we said, what is the largest triangle-free subgraph of the complete graph on n vertices? Now, since we're studying things which are relative to some other graph, then it is natural to start by defining the extremal number of the triangle relative to some graph G. So this will be defined as the largest number of edges in some graph G prime, which is a subgraph of G and still doesn't contain a triangle. And let's observe that for any graph G, this extremal number of the triangle relative to G is at least half of the number of edges of G. So note that this is very close to half of all the edges of Kn, and one of the inequalities is true for every graph. So who can tell me why is this inequality true? Don't be shy. Yeah, you can just take the largest bipartite subgraph of G. It will not have a triangle, and it's well known that every graph contains a bipartite subgraph of at least half of the edges. I mean, you can either take, say, a random bipartition, this is the expected number of edges that will cross it, or you can take the largest one, and the largest one is always unfriendly in the sense that every vertex is at least as many neighbors in the other part as it is in its own part, because otherwise you could move it over and increasing the number of edges in the bipartition. And something kind of more general is true, and this will be one of your exercises, is to prove that for all graphs G and H, where G has n vertices, and we think of H as a fixed graph. I hope this notation is self-explanatory. So this is the largest number of edges in an H-free subgraph of G. So this is at least so the proportion of edges of G that you can have in an H-free graph is at least as large as it is in the complete graph. So this is even ever slightly stronger than that, because the complete bipartite graph is slightly more than half of the edges of the Now, if this is true for every graph, then it will be true for our random graph with probability 1. It's true for each possible outcome. And then the question becomes, or the natural question to ask here is, for what values of the edge probability P, is it true that we can reverse this inequality and this will hold with probability which is close to 1? And so, formal question. For what P where it is important that we would allow P to be a function of n, so the edge probability can depend on the number of vertices, and we usually think that it will decrease to 0 as n tends to infinity. This leads to more interesting questions. So for what P does it hold? That the largest subgraph, triangle-free subgraph of the binomial random graph G and P is asymptotically half of its expected number of edges. And that this holds asymptotically almost surely, which is standard jargon in the random graph theory. So I don't want to write asymptotically almost surely. This will cost me too many minutes from from the course, so I will abbreviate by AAS, and this means that this probability tends to 1 as n, which is the number of vertices, tends to infinity. So in fact, I will ask this question for all n at the same time, and for every n, you have a different random graph, and this event has some probability, which is a function of n, and then we want to ask, when does this probability tend to 1 as n tends to n? And also, I didn't write here the number of edges of GNP, but rather the expected number of edges. However, when the edge probability P is not too small, then the number of edges in GNP is concentrated around its expectations of these two questions, because we're only asking things, so things with positive probability close to 1, they will be equivalent. In fact, which means that given this observation, we know that this is at least always at least half of the number of edges of GNP, which is at least half of the expected number roughly of edges of GNP. So one of these inequalities we get for free, and the question becomes, for what P does GNP not contain a triangle-free subgraph which is substantially larger than half of this number of edges? So this is the real question. The lower bounds. One and a half minus the lower one. Entries to P follows as the number of edges from GNP is equal to asymptotically equal to n choose to P as long as P is not very small. So P divided by 1 over n squared tends to infinity. Okay, I'm going to erase at least one of the boards, and meanwhile, if you have any questions, then please do ask. So the second question will concern Ramsey's theorem, and the question is under what assumptions on P does the statement of Ramsey's theorem hold relative to G. And precisely we ask, let us write G arrows K3 in R colors. And this will mean that however we choose a function phi, which will assign to every edge of G a number between 1 and R, so we will color every edge in R colors. Then we want for each such coloring to have a color I between 1 and R, so that if we look at all the edges, so the pre-image of I, all the edges colored I, we get some subgraph of G, and we want this subgraph to contain a triangle. So Ramsey's theorem is that if n is sufficiently large, then Kn arrows K3 in our colors. And the formal question is, for what P does the relation G and P arrows K3 in our colors hold asymptotically, almost surely, meaning with probability tending to 1 as n tends to. And in fact, this was the question that was originally studied in the context, and the reason why people were interested in this is actually very nice motivation. If you've ever seen Ramsey's theorem kind of in a mathematical setting, probably any introduction starts as follows. You have 6 people at a party, and every pair either knows one another or doesn't know or don't know one another. Prove that regardless of the acquaintances or non-acquaintances, you will always find 3 people that either pairwise know one another or pairwise do not know one another. Which is just to say that K6 arrows K3 in 2 colors. With 2 colors, the edges of the complete graph of 6 vertices, and for every coloring, we have a triangle. Now, this means that if I take any graph G which contains a K6, then it also arrows K3 in 2 colors, because I can just ignore the colors of all the other edges outside of this K6, and I will find a triangle there. And a Hungarian mathematician that you also might know, Paul Erdős, asked, okay, can you find a graph which has this property but doesn't contain a K6? Maybe the fact that this happens is precisely because you have 6 vertices that are pairwise connected. And then he said, okay, so if we're asking no K6, then why not ask no K5? And since we're asking no K5, then why not ask no K4? Since we're asking no K4, why not ask no K3? Well, of course, we cannot ask no K3 because we're looking for a monochromatic K3, so at least we need to have one triangle. So the question was, can you find a graph G which doesn't have a K4, but no matter how you 2-color its edges, you will have a monochromatic triangle? And he even offered money for it. I think first he offered $100 to find such a graph which is less than 10 to the 10 vertices. And someone constructed such a graph, and the way this graph was constructed, so I think there was this kind of sequence of improvements. First, maybe it was 10 to the 10 to the 10, someone got $100, and then he asked, okay, let's be more greedy, what about the million? And you will see in the exercises that you can prove the existence of such graphs by considering the random graph at the appropriate density. This was done by Frankel and Rudel in '86. It will be kind of one of the early examples here of how to kind of attack these questions. And the world record today is below 1,000. I think it was 2,000, Dudek and Riddle, they even got $50 for it. It was after Erdős had died, you can still get it. So I'm not going to offer any monetary prize for solving the exercise. Yes, so let me just write motivation. Find a graph G such that even though it doesn't have a K4, however you color its edges, you will have a triangle. So in fact, we will show, or you will be able to show more that we'll have a graph without a K4, but if you R color its edges, you will also find the triangles. For every R, you will find such a graph. It's not, there's nothing special here about 2 colors, but maybe, of course, the number of colors is 1 billion, but you can't expect to find such a graph on 1,000 vertices. You will have to grow with the number of colors. And there's yet another type of statements that we will study, and this is the study of typical triangle free graphs. So what we've been discussing so far is let's say things about the largest triangle-free graph. So we say in the complete graph, the only largest triangle-free graph is the balanced complete bipartite graph. And Ramsey's theorem says take the complete graph, you cannot decompose, even though the largest triangle-free graph contains half of the edges, you cannot split it into 10 triangle-free graphs. And kind of the final type of question that I'll discuss in the course is take the collection of all triangle-free graphs and pick one uniformly at random. What does it look like? What can you say? Can you say anything meaningful about the structure? Or you can kind of be slightly more precise. You will not only fix the number of vertices in the graph, but also the number of edges. So now pick uniformly at random a triangle-free graph with n vertices and m edges. Pick one at random. What can you say about this structure? Any question? What can be said about a typical triangle-free graph? And more precisely, that is, draw an Fn from the family of all triangle-free graphs on the vertex set n uniformly at random. Uniformly at random, which means at random uniformly means every graph with the same probability, or perhaps f and n from f and mk3, which we will define as the collection of all triangle-free graphs on the vertex set n that moreover have precisely m edges, so from edge of k we take n uniformly at random. What is the structure of this Fn or of f and m? And as you will see in the course, that usually doing this, the answer is what is the structure, and the answer, I'm paraphrasing here, one of my colleagues, Gadi Kozma, a random triangle-free graph is boring, because a random triangle-free graph is triangle-free for trivial reasons, namely it's bipartite. And this was proved in 1976. And even though a random triangle-free graph is boring, then proving that a random triangle-free graph is boring is not necessarily boring. Right. And well, start 1976. It states that almost all triangle-free graphs are bipartite. That is, if we look at the family of all triangle-free graphs, and intersect it with the family of bipartite graphs. In fact, every bipartite graph is triangle-free, but I want to write it in this way deliberately, so it's even clearer. So this is the number of triangle-free graphs that are bipartite, and we compare it with the number of triangle-free graphs. So this is draw one at random, everyone is probability 1 over fn k3, and this is the probability that a random triangle-free graph is bipartite. Now, the limit of this probability is n tends to infinity is equal to 1. So this is precisely what they mean by almost all triangle-free graphs are bipartite, the proportion of bipartite graphs among all triangle-free graphs with the given number of vertices tends to 1 as the number of vertices tends to infinity. And a corollary of this is that we can say something about the number of triangle-free graphs. So triangle-free graphs, it's not clear how to count triangle-free graphs. It's pretty clear how to count bipartite graphs. How do you count bipartite graphs? Well, you can give kind of an easy upper bound by saying, if a graph is bipartite, so the theorem says that the number of triangle-free graphs is actually the same as the number of bipartite graphs, because every bipartite graph is triangle-free, and most triangle-free graphs are bipartite. So here we have actually an equality. How do you upper bound the number of bipartite graphs? Well, a graph is bipartite means that there must be some partition of the vertices into two sets A and B. And now, how many bipartite graphs are with the given bipartition? Well, there's A, size of A times size of B, possible edges to include or not include, and we can either include or not include any of them. So this is exactly the number of bipartite graphs with the bipartition A and B, and we are kind of overcounting some of the graphs, but it's actually not too bad. And now we have at most 2 to the n bipartitions, and each of these terms is at most the maximum 2 to the k times n minus k. If the set A has k vertices, the set B has n minus k vertices, so each term is bound by the maximum of this. And this is probably already familiar because this appeared in the definition, so not the definition, the statement of Mantel's theorem. So this is equal to 2 to the n plus the extremal number for the triangle. I'm sorry, I should have added a 1 plus window of 1 everywhere. Now, how good is this bound? This bound is actually not too bad because the number of triangle-free graphs will always, what we can do is take the largest one, which has this many edges, and each of its subgraphs is also triangle-free, so this gives us a lower bound. So we have an upper bound and a lower bound, two numbers whose logarithms are asymptotically the same. So, and this gives that the logarithm of this number, maybe say x2, is asymptotically equal to the extremal number. So, and we will see that it's a more general phenomenon in kind of many of these questions. It turns out that the logarithm of the number of structures is kind of intimately related to the largest size of of a structure. So the logarithm of the number of triangle-free graphs is intimately related to the largest size of the triangle. And this is a more general phenomenon. Okay. I'm going to switch gears a little. So if you have any questions, please, this would be a great time to ask.
In this setting, the personal tuplets say if there is an isoborg.
No, this is a very good question. So in the entire lecture series, I will be speaking about labeled graphs. That I specified that all these triangle-free graphs have a given vertex set 1 up to n, and isomorphic graphs, which are different as labeled graphs, I treat as different graphs. So in particular, we're counting here over all bipartitions and not only over all sizes of bipartitions.
So here you use the fact that the extremal number, the prime number is quadratic, right? Because the n term.
Yes. Mm-hmm. Right. That he was de facto right. Mm-hmm. But if we had, this is a pretty good error term here, this 2 to the n, but in a more abstract setting, we would only be able to prove this thing with this n replaced by little o of n squared. So today or tomorrow, I will prove this upper bound, but not with n, but rather with little o of n. Without using, I mean, of course, without using the Erdős-Kleitner rules right here. Okay, so let's continue. I think from an educational point of view, I mean, I could first say, hey, this is how you prove it, but I deliberately said to myself, okay, let's try to together try to attempt to prove it and see why it fails and learn from this and try again and learn from this and try again until we arrive to the solution. And the advantage will be able to do it in 1 hour, and in practice this took many years, but yeah, this is how it is. And the title for the discussion is the failure of union bounds. If you ever worked with random graphs or random anything, your first instinct when you try to bound some random variable, which is combinatorially defined, is to use the union bound. Now, what we would like the question that I'll focus on now is this Mantle's theorem relative to GNP. So we're trying to estimate this random variable. We already have a good lower bound that holds with probability very close to 1. It's at least half of the expected number of edges asymptotically. So we want to now prove an upper bound for it. Since we want to prove an upper bound for it, this is the same as saying, let's bound from above the probability that this is large. So we'd like to bound from above the probability that this happens. And we have some kind of natural guess for n, but let's kind of not assume what type of bound we want to prove. Let's prove some bound for some n. Now, this event is the same. What does it mean that the extremal number of triangle in GNP is at least n? It means that GNP contains a triangle-free subgraph with n edges. So this is the same as saying GNP contains subgraph G, which is triangle-free has n vertices and n edges. And this already suggests a union bound, right? Let's just union bound over all subgraphs. So we can now, this probability is at most the sum over all possible graphs G of the probability that G is contained in G and P. Now, what is the probability that a graph is contained in G and P? Since the edges are independent, it's P to the number of edges of the graph that we're trying to find. Right, because we need all the edges and the edges appear independently. So this is equal to the sum over all G in the family, P to the number of edges of G. However, all these graphs have the same number of edges, M. So this is equal to the size of the family times P to the N. Great. And how good is it? And unfortunately, this is pretty bad. Why is it pretty bad? I mean, I'm going to do something strange. Let's lower bound it. How many graphs are there that are triangle free, have n vertices and n edges? What we could do is take some graph, which is a subgraph of Kn. So one of the largest graphs that are triangle free. And however we choose m edges from it, we get an m-edged graph, which is also triangle free. So this is a lower bound on our upper bound. But this binomial coefficient is kind of one of great inequalities in combinatorics is this inequality. A choose B is bounded from above by EA over B to the B. And in fact, if B is much smaller than A, then this is pretty close to the truth. So since we'll be mostly interested in sparse random graphs, then this n that we're looking for will be subquadratic. So this will be very close to E times the extremal number divided by n to the n. And we also have the P to the n. So I can stick it at P. Of course, if this will tend to 0, this has to tend to 0. But when does this tend to 0? We need m to be at least E times the extremal number times P. So this would work only if m is at least E times the extremal number times P. But E times the extremal number, this is E roughly E over 2 times n choose 2P. And E over 2 is like 1.3 or 1.35. So this bound is completely useless because we can't even prove that the largest triangle free graph has of GNP has at most as many edges as typically we know GNP has. So this is kind of a big fail. But maybe we learned something from this. We probably learned that we wouldn't be able even to prove using this fact that GNP doesn't contain any subgraph which is n choose 2, which is significantly more than n choose 2P edges. And from this failure of union bounds, one thing that's kind of a take-home message will be that first we should maybe revisit how we prove concentration for the number of edges of GNP, because we certainly can't approach it this way. And kind of I want to use this opportunity to recall some basic concentration inequalities for binomial random variables. So just recall here, and if you haven't seen them, or if you haven't proved them, then I'll give you the opportunity to prove it in the exercises. So how do we, so I said here that the number of edges in GNP is concentrated around the expectation, but what we, if you don't know this fact, then we need to see how to prove it. So the theorem that we'll use repeatedly, which is first stated in this form by Hofding in 1963. However, it's essentially proved by Chernoff in the 50s. And actually, the same proof method was already known in the 1920s. A Russian mathematician named Berestein it was the first to use this method to prove concentration and quality. And the theorem says, however I choose P and Q between 0 and 1, then the probability that a binomial random variable n trials with success probability P exceed n times Q. This is called exponential in minus n times some function that depends on P and Q, and this I P Q is Q log Q over P plus 1 minus Q log 1 minus Q divided by 1 minus. So I stated in this way because this is the best constant you can get in the exponent, but maybe this is not the most useful way of stating it because you need to understand something about this function. And a corollary will be that for every first delta between 0 and 1, the probability that a binomial random variable NP is at most 1 minus delta times its expectation, which is NP. This is at most exponentially small in delta squared NP over 2. And for every positive delta now, for deviations in the upper tail, the probability of overshooting the expectation by 1 plus delta is at most exponential in minus delta squared NP divided by 2 times 1 plus delta over 3. And I would like you to, if you haven't seen this, this is a great exercise, and I'll give you a hint of how to prove it. So, proving this is a really great exercise. Deriving the corollary from this is, I mean, you need to just estimate this function. This is anywhere. It's simple but not easy exercise in calculus. Okay, so one reason we failed here is that we didn't use the right methods to prove the concentration for the number of edges. So now we already know how to prove a good bounds on the probability that the GNP will have too many edges or too few edges. So let's try now to use it to our advantage. So I'll now give you a second union bound argument, which will use this but will still fail. A better union bound. Now, the better union bound comes from the following observation. Every triangle-free graph is contained in some maximal triangle-free graph. What do I mean by a maximal triangle-free graph? I mean that you can no longer add any edges because every edge that is not in the graph will close the triangle with edges that are already in the graph. Every triangle-free graph is contained some maximal triangle-free graph. Maximal, inclusion maximal, you can no longer add any edges without creating triangles. So let's define this notation. So this will be all the graphs which are triangle free, such that when you take any edge which is not in G and add it to G, then this already contains a triangle. And how can we now use this definition or this idea to give an upper bound on the probability that and that G and P contains a triangle-free subgraph with at least n edges. And actually, this gentleman is a specialist on maximal triangle-free graphs. And now I can say that use the union bound now, since every graph, triangle-free graphs contain a maximal triangle-free graph. If G and P contains some triangle-free graph which is m edges, this graph is contained in some maximal triangle-free graph. Now, in particular, the number of edges in it cannot be larger than the intersection of G and P with this maximal triangle-free graph. So we can now sum union bound over all the maximal triangle-free graphs of the probability that the intersection of G and P with our maximal triangle-free graph P is at least m. Now, every maximal triangle-free graph, of course, cannot have more edges than a largest triangle-free graph. So note that the number of edges of P is certainly no more than the largest number of edges in a triangle-free graph. And therefore, if we take n now to be 1 plus delta times the extremal number of K3 in n times P, so this is the n that we would really like to stick in here, then this is at most the sum over all T, which are maximal triangle-free graphs. And it's at most the probability we're intersecting G and P with a fixed graph with E of T edges, which is at most that. And this number of edges is a binomial random variable, which has ET trials, success probability P. So it's the binomial random variable, ET, success probability P, at least n. So this is actually an equality. However, the ET is at most this extremal number, so I can bound it from above if I increase the number of triangles. But the M now is 1 plus delta times the expectation of this variable. So by our second corollary, we know that this is already exponentially unlikely. So this is at most for each element of this family, we get something, some constant that depends on delta times n squared b. And it looks great because the probability estimate here is really, really good. However, there's a problem. There's just really many maximal triangle free graphs. And this will be, yes, much better. This will be one of your exercises. Prove that the number of maximal triangle free graphs on n vertices is at least exponential in n squared over 8 minus little of x. And I mean, if I state it like this, it would be a very difficult problem, but let me tell you how to start. So hint, how do you find so many maximal triangle free graphs? I will assume that n is divisible by 4. Split the vertex set into 2 sets of equal size. N is divisible by 4, so each of the sets is even. And in A, I will put a perfect matching. So here there's n over 4. Disjoint edges. Now, there will be no edges inside B, and these are all the edges I put inside A. And I will get a large family by choosing what to put in between. And how do you choose? For every vertex in B, so little b in B, B will choose exactly one of the neighbors in each edges of the matching. So for every B in B, B is adjacent to exactly one endpoint in every edge of the matching. This way, certainly we don't have any triangles, because any triangle would have to involve an edge in the matching and a vertex from here. But every vertex from here only chooses one endpoint from every edge of the matching. So for sure, no graph here has triangles. And the number of possible graphs is there are n over 2 vertices. Each of them makes n over 4 independent choices. So the number of such graphs is 2 to the n squared over 8. And you can prove, in fact, that with probability tending to 1, this graph will be maximal triangle free. You won't be able to add any edge here without closing a triangle. So certainly you cannot add any edge from B to the other side, because from each edge of the matching you already picked one endpoint, so this would close a triangle, but possibly you could add some edges in here or some edges in here, and the exercise to prove that typically you won't be able to do it. And if you want to learn more things about maximal triangle free graphs, then we have an expert there in the audience. So great. We have exponential n squared over p, exponential n squared, and still the second attempt fails. So there's just too many maximal triangle graphs. And kind of this brings me finally to a third method which will work. This is the right argument, but there's just too many maximal triangle free graphs that we use to cover all the graphs in which are triangle free. So kind of the idea behind the container method is to find a better family that will kind of cover all the triangle free graphs. We won't be able to do it with triangle free graphs themselves because we would have to take all the maximal ones. There's just too many of them. But there is a covering all triangle free graphs, which is much, much smaller than the maximal triangle free graphs. But for many purposes, it's not much worse. And I call it container theorem for triangle free graphs. A weak version. So the reason why I wrote weak version will only be clear after I will state the strong version. But just to signify that this is not the final product. So what does the theorem say? The theorem says that you give me some small positive epsilon. And the theorem gives you a C. Such that the following holds for all n. The theorem postulates the existence of a family Gn, which will replace the family of maximal triangle free graphs. So it's a family of subgraphs of Kn. With the following properties. One is, as with maximal triangle free graphs, every triangle free graph is contained in one of the graphs in Gn. So each F in the family of triangle free graphs is contained in some G in Gn, hence the name container.
You mean it's a subgraph, right?
Right. Yes, as a subgraph, yeah. Two, each G, each subgraph in the family, perhaps it's not triangle free, but it's not far from being triangle free. So it contains fewer than epsilon n cubed triangles. And why n cubed? And because the complete graph has roughly n cubed over 6 triangles, n choose 3. And here we say that these graphs contain a tiny fraction. You should think of epsilon as a very small constant, just a tiny fraction of all the triangles available at Kn. And 3, here still, the set of maximal triangle 3 graphs still has both of these properties, but the final property is that Gn is not too large. It's much, much smaller than the family of maximal triangle 3 graphs. Its size is exponential in n2 3/2 log n. Still a lot, but we're comparing it to something which is exponential in n squared. Note that 1 and 2 are easy to satisfy simultaneously, and 1 and 3 are also easy to satisfy simultaneously because I could take Gn to comprise just the complete graph itself. It contains all triangle 3 graphs, and it's just there's one subgraph. So in some sense, this family Gn interpolates between the complete graph and the family of maximal triangle 3 graphs. So this Gn interpolates between the family comprising just the complete graph and the family of maximal triangle 3 graphs. Now, this family, I mean, this condition, even though it's natural and makes sense, it's still a little bit mysterious, because in all these questions before, we're interested not in the number of triangles, which is almost always 0, but rather in the size of this triangle 3 graphs. And a famous theorem due to Erdős and Simonovic said that any graph that has at most or fewer than epsilon n³ triangles cannot be much larger than the largest triangle 3 graph. So this will be able to tell us that also these graphs in G, like in here, we knew that they're triangle 3 and therefore they contain at most this many edges, but this is still true if you only assume this weaker condition, you can get an approximate inequality. And this will be the next theorem that I will state. And since it's already 4:25 a.m. in Poland, I won't be able to prove it today, but we'll prove it tomorrow. A theorem. Erdős. Simonovic from 1983, and it's usually called the supersaturation theorem. It says the following: for every delta positive, there exists an epsilon, which is positive, such that every n vertex right with at least whose number of edges exceeds the largest number of edges in a triangle by an additive delta n squared must contain at least epsilon n triangles. And we're interested in the contrapositive, meaning every n vertex graph which has fewer than epsilon n triangles has fewer than the extremal number plus delta n squared edges. Okay, and let me finish by just one simplest application in algebra It's the corollary of the Erdős, Kleitman, and Rothschild period, 1976. We will prove that the number of triangle free graphs on the vertices is at most 2 to the extremal number, which is a trivial lower bound, and we'll be able to add only this little O n squared in the exponent. So just to kind of illustrate how these things go together. And here's how the proof goes. We will pick any positive delta. This will be the little O. So we'll prove it for every delta. And what Erdős and Simonovich give us is they supply a positive epsilon. And we feed this epsilon to the container theorem for triangle free graphs. And we get the constant C. And more importantly, we get the family Gn of containers for every n. Now, let's count all the triangle free graphs. So every triangle free graph is contained in one of the containing graphs. So we can sum now over all these containers, G and Gn, and just count those ones which are contained in this containing graph. And we're sure that we cover each of them at least once. And here, let's now forget that these were triangle free graphs and just upper bounded by the number of all subgraphs of G. So it's 2 to the number of them. Now, this graph G has fewer than epsilon n cubed triangles. So Erdős and Simonovich tell us that it must have fewer than this number of edges. So this is at most, this is by Erdős, Simonovich, and 2. This was true by 1. It's the size of Gn, and none of these terms is larger than 2 to the extremal number for the triangle plus delta n squared. But we also know that Gn is actually pretty small. It's only exponential in n to 3 halves log n. So this is at most 2 to the power ex and a3 plus delta n squared plus c log base 2e and 3 halves log n. However, this will be at most delta n squared if n is sufficiently large as a function of c and delta. So we got 2 ex and a3 plus 2 delta n squared. And then we just take delta to 0, and this gives us 2 to ex and a3 plus little o of x squared. And yeah, it's 11:30, so I'll stop for today. Thanks.
Any questions?